What if everything we've ever observed in the universe, every star, every galaxy, every shimmering speck of light, is just the tip of the cosmic iceberg? The truth is, the observable universe we know and study is only a sliver of what's really out there. Beyond the reach of our telescopes lies a vast, invisible tapestry known as the cosmic web, a sprawling network of galaxies, dark matter, and dark energy that stretches far beyond what our eyes can see. It's the backbone of the universe, the hidden architecture that shapes everything we've ever known. But here's the thing, as much as we've learned, we've barely scratched the surface. What lies beyond the edges of what we can observe? How does this cosmic web define the very fabric of reality? And what secrets does it hold about the universe's origins, its fate, and our place within it? In this video, we're going to venture beyond the observable, exploring the boundaries of the cosmic web to uncover the mysteries that lie in the shadows of the cosmos. Get ready to question everything you thought you knew about the universe, because what's out there might just change the way you see everything. Imagine a spiderweb, glistening with dew, stretching across a vast forest. Now, picture that same intricate web, but on a scale so enormous, it spans the entire universe. This is the cosmic web, the invisible framework that holds everything together. It's not just a structure, it's the universe's backbone, a sprawling network of galaxies, gas clouds, and dark matter, all woven together in a delicate yet unimaginably vast tapestry. From the densest galaxy clusters to the emptiest voids, the cosmic web connects everything, forming the largest structure we've ever discovered. But how did we come to understand this colossal network? It wasn't through direct observation, at least not at first. Instead, scientists pieced together its existence through a combination of computer simulations and painstaking observations. These simulations revealed how dark matter, an invisible and mysterious substance, acts as the scaffolding for the web, pulling galaxies and gas into its threads over billions of years. Observations of distant galaxies and the faint glow of hydrogen gas further confirmed this cosmic architecture, showing us how the web shapes the universe's evolution. To help visualize this, think of the cosmic web as a city's subway system. Just as subway lines connect neighborhoods, the web's filaments link galaxies, allowing them to interact and grow. And just as some stations are bustling hubs while others are quiet stops, some regions of the web are dense with galaxies, while others are eerily empty, the cosmic voids. But studying this immense structure isn't easy. It's like trying to map a spider web from 1,000 miles away. So, how do scientists uncover its secrets? The answer lies in the tools they use: telescopes that peer into the farthest reaches of space, simulations that recreate the universe's birth, and even the subtle distortions of light caused by the web's gravitational pull. Each tool offers a new perspective, helping us piece together the story of this universe-spanning network. Now, let's zoom in on the invisible force that holds this cosmic web together: dark matter. It's the universe's hidden architect, a mysterious substance that doesn't emit, absorb, or reflect light, making it completely invisible to our telescopes. Yet its presence is undeniable. Without dark matter, the cosmic web as we know it wouldn't exist. Its gravitational pull acts like an invisible glue, shaping the filaments and nodes that define the web's structure. Think of it as the scaffolding of a skyscraper, unseen, but absolutely essential to keeping everything standing. But how do we study something we can't see? Scientists have had to get creative. One of the most powerful tools in their arsenal is gravitational lensing. This phenomenon occurs when the immense gravity of dark matter bends the light from distant galaxies, acting like a cosmic magnifying glass. By observing how light warps around these invisible masses, researchers can map the distribution of dark matter, revealing the skeleton of the cosmic web. Another method involves analyzing the cosmic microwave background, the faint afterglow of the Big Bang. Tiny fluctuations in this ancient light provide clues about how dark matter influenced the early universe, helping us understand how the web formed over billions of years. Here's a mind-blowing fact. Dark matter makes up roughly 85% of the universe's total mass. That means everything we can see, stars, planets, galaxies, accounts for just a small fraction of what's out there. The rest is this enigmatic substance, silently shaping the cosmos. It's a humbling reminder of how much of the universe remains hidden from our view. And while dark matter holds the cosmic web together, there's another invisible force at work: dark energy. This mysterious energy is driving the expansion of the universe, stretching the web's filaments farther and farther apart. But that's a story for the next part of our journey. For now, let's marvel at the invisible threads of dark matter, weaving the grand tapestry of the cosmos into existence, and ponder what other secrets might be hiding in the shadows of the universe. If dark matter is the cosmic web's invisible glue, then dark energy is the force that's pulling it apart. Picture this: a universe where galaxies aren't just drifting away from each other, they're being pushed apart at an ever-increasing speed. That's the power of dark energy, a mysterious force that makes up about 68% of the universe's total energy. Unlike gravity, which pulls things together, dark energy works in the opposite direction, stretching the fabric of space-time itself. It's as if the universe has a hidden engine, constantly revving up, driving galaxies farther and farther apart. So, how did we stumble upon this strange force? The story begins with distant supernova, exploding stars that serve as cosmic mile markers. In the late 1990s, astronomers studying these supernovae made a startling discovery. Instead of slowing down as expected, the universe's expansion was speeding up. It was like throwing a ball into the air and watching it fly faster the higher it went. This unexpected acceleration could only be explained by the presence of a force counteracting gravity: dark energy. But what exactly is dark energy? The truth is, we don't fully understand it yet. Some theories suggest it's a property of space itself, woven into the very fabric of the universe. Others propose it could be a new kind of field or energy that permeates everything. What we do know is that its effects are profound. Over billions of years, dark energy has been stretching the cosmic web, pulling galaxies apart and thinning out the filaments that connect them. This raises a tantalizing question: what does the future hold for the cosmic web? If dark energy continues to accelerate the universe's expansion, will the web eventually unravel? Some scientists speculate that, in the distant future, the threads of the cosmic web could be stretched so thin that galaxies become isolated, drifting alone in an ever-expanding void. It's a haunting possibility, one that challenges our understanding of the universe's ultimate fate. Yet, even as dark energy pushes the boundaries of the cosmic web, it also highlights the limits of what we can observe. The observable universe, the portion we can see and study, is just a tiny fraction of the whole. Beyond that lies a vast expanse, stretching far beyond the reach of our telescopes. What's out there? Are there other cosmic webs, other structures, other universes entirely? These are the questions that push us to explore further, to peer deeper into the shadows of the cosmos. As we stand on the edge of the observable universe, looking out into the unknown, one thing becomes clear: the cosmic web is more than just a structure. It's a story of how the universe began, how it evolved, and how it might end. And while dark energy may be stretching that story in ways we can't yet fully comprehend, it's also a reminder of how much we still have to learn. The universe, it seems, is always one step ahead of us, holding its secrets close, waiting for us to uncover them. The observable universe is like a vast stage, illuminated by the light of countless stars and galaxies. But here's the catch: it's only the portion of the cosmos we can see from Earth, a tiny slice of the whole. This boundary isn't arbitrary, it's defined by two key factors: the speed of light and the age of the universe. Light travels fast, but it's not instantaneous, and the universe has only been around for about 13.8 billion years. That means the farthest light we can see has been traveling for that same amount of time, creating a kind of cosmic horizon beyond which light hasn't reached us yet. Think of it like a ship sailing across an endless ocean. As the ship moves forward, the horizon always seems just out of reach, no matter how far it travels. Similarly, the cosmic horizon marks the edge of what we can observe, a boundary that shifts as time passes but never fully disappears. Beyond this horizon lies the unknown, a vast expanse of the universe that remains hidden from our telescopes and our understanding. This raises a fascinating question: what lies beyond the cosmic horizon? Could the universe stretch on infinitely, filled with galaxies and structures we'll never see? Or is there something else entirely, regions of space and time that defy our current understanding of physics? The truth is, we simply don't know. The observable universe is just the beginning, the part of the cosmic story we're able to read. Beyond it, the narrative may continue in ways we can't yet imagine. But here's where things get even more intriguing. The universe's expansion, driven by dark energy, means that some galaxies are moving away from us faster than the speed of light. That doesn't violate the laws of physics, because it's space itself that's stretching, not the galaxies moving through it. As a result, these galaxies are crossing the cosmic horizon, disappearing from our view forever. It's as if the universe is slowly turning off the lights, one by one, in the distant reaches of space. This cosmic horizon isn't just a limit, it's a reminder of how much of the universe remains hidden from us. It challenges us to think bigger, to question what lies beyond our view, and to push the boundaries of what we can observe. And while we may never see beyond that horizon directly, we can use the tools of science, like theories, simulations, and indirect observations, to explore the possibilities. So, as we stand on the edge of the observable universe, peering into the unknown, we're left with a profound sense of wonder. The cosmos is far grander than we can ever fully grasp, filled with mysteries that stretch far beyond the reach of our telescopes. And perhaps in that vast expanse beyond the horizon lies the next great discovery, a clue to the universe's origins, its ultimate fate, or even our place within it. The journey to uncover these secrets has only just begun. What if the universe is far grander than we can ever imagine? Beyond the cosmic horizon, the edge of what we can observe, lies the unobservable universe, a realm so vast and mysterious that it defies comprehension. While the observable universe spans an astonishing 93 billion light-years across, it's just a tiny fraction of the whole. Beyond it, the cosmos stretches on, possibly infinitely, filled with galaxies, structures, and phenomena we may never see. But what could be out there? One compelling idea is that the cosmic web, the sprawling network of galaxies, dark matter, and filaments we've come to understand, extends far beyond our horizon. Imagine this web repeating itself on scales so vast that entire galaxy clusters become mere specks in an even larger pattern. Some cosmologists theorize that the universe could be infinite, with structures repeating endlessly, like a cosmic fractal. It's a humbling thought. The galaxies we see might be just one small piece of an unimaginably larger puzzle, but the unobservable universe could hold even stranger possibilities. What if it's home to exotic forms of matter or energy, completely unlike anything we've encountered? Some theories suggest the existence of dark galaxies, structures made entirely of dark matter, invisible to our telescopes but shaping the cosmos in profound ways. Others propose the idea of parallel universes, entire realms existing alongside our own, separated by dimensions we can't perceive. These ideas, while speculative, remind us how much of the universe remains hidden from our view. As cosmologist Janna Levin once said, "The universe is not only stranger than we imagine, it's stranger than we can imagine." This quote captures the essence of our quest to understand the unobservable. It's a reminder of the limits of human knowledge and the boundless nature of the cosmos. So, how do scientists probe these mysteries? The answer lies in a combination of cutting-edge tools and creative thinking. Telescopes like the James Webb Space Telescope allow us to peer deeper into space and time, capturing light from the earliest moments of the universe. Simulations run on supercomputers recreate the universe's evolution, offering glimpses of what might lie beyond our horizon. And indirect observations, like studying the cosmic microwave background or gravitational waves, provide clues about the universe's hidden structure. Each tool is like a key, unlocking a small piece of the cosmic puzzle. While we may never directly observe the unobservable universe, these methods allow us to infer its existence and explore its possibilities. It's a testament to human ingenuity, the ability to reach beyond the limits of our senses and uncover the secrets of the cosmos. As we contemplate the vastness of the unobservable universe, one thing becomes clear: the journey of discovery is far from over. Every new observation, every breakthrough in theory, brings us closer to understanding the true scale and nature of the cosmos. And while the answers may lie beyond our horizon, the questions themselves inspire us to keep exploring, to keep wondering, and to keep pushing the boundaries of what we know. Telescopes like Hubble and the James Webb Space Telescope are our eyes into the depths of the cosmos, allowing us to glimpse the faintest threads of the cosmic web. These incredible instruments don't just capture light, they capture time itself, revealing galaxies as they were billions of years ago. By observing the light from these ancient galaxies, astronomers can map the distribution of matter across vast distances, piecing together the intricate structure of the web. It's like reconstructing a jigsaw puzzle where each piece is a galaxy, and the picture it forms is the universe itself. But telescopes are only part of the story. To truly understand the cosmic web, scientists rely on another powerful tool: supercomputer simulations. These simulations recreate the universe's evolution from its earliest moments, modeling how dark matter and gas coalesced into the filaments and nodes we observe today. One groundbreaking example is the Millennium simulation, which traced the growth of the cosmic web over 13 billion years, revealing how galaxies form and cluster along its threads. These virtual universes, built with equations and algorithms, provide a laboratory for testing theories and uncovering the hidden mechanisms that shape the cosmos. Combining observations with simulations has led to some of the most exciting discoveries in modern cosmology. For instance, by studying the light from distant quasars' bright cores of ancient galaxies, Astronomers have mapped the Webb's hydrogen gas filaments, invisible to our telescopes. This discovery confirmed that the cosmic web isn't just a theoretical construct. It's a real, tangible structure that defines the universe's architecture. Yet, studying the cosmic web isn't without its challenges. The sheer scale of the universe makes it difficult to capture the web in its entirety. Imagine trying to photograph a city from space while standing on a single street corner. It's a daunting task. Add to that the limitations of our telescopes, which can only observe a fraction of the universe's light, and the complexity of interpreting simulations, and you begin to see the hurdles scientists face. Despite these challenges, the quest to understand the cosmic web pushes the boundaries of human knowledge. Each observation, each simulation, brings us closer to unraveling the mysteries of the universe's largest structure. And as our tools grow more advanced, so too does our ability to explore the hidden depths of the cosmos, revealing not just the universe we know, but the universe we have yet to discover. Studying the cosmic web is like trying to map an invisible city in the dark. Its vastness alone is staggering, a network of filaments and voids stretching across billions of light years, far beyond the reach of our most powerful telescopes. But the challenges don't stop there. One of the biggest hurdles is the web's hidden architect, dark matter. This mysterious substance doesn't interact with light, making it completely invisible to our instruments. Yet without it, the cosmic web as we know it wouldn't exist. It's like trying to study a sculpture by only seeing its shadow. You know it's there, but its true form remains elusive. Then there's the sheer scale of the universe itself. The cosmic web spans distances so immense that even light takes billions of years to travel from one end to the other. This means that when we look at distant galaxies, we're seeing them as they were in the past, not as they are today. It's like trying to piece together a puzzle where the pieces are constantly moving and changing. And let's not forget the limitations of our technology. Even the most advanced telescopes, like the James Webb Space Telescope, can only capture a fraction of the universe's light. Much of the cosmic web's structure is hidden in the faint glow of hydrogen gas or obscured by dust and cosmic debris. It's as if we're trying to read a book with half the pages missing. Yet, these challenges haven't stopped scientists from pushing the boundaries of what's possible. Take the story of Dr. Jocelyn Bell Burnell, who, while analyzing data from a radio telescope in the 1960s, discovered pulsars rapidly spinning neutron stars that emit beams of radiation. Her groundbreaking work not only revealed a new class of celestial objects, but also demonstrated how perseverance and innovation can overcome seemingly insurmountable obstacles. Today, astronomers use similar ingenuity to study the cosmic web, developing new techniques like gravitational lensing and advanced simulations to map its hidden structure. These efforts are driving innovation in astronomy and astrophysics, leading to discoveries that reshape our understanding of the universe. For example, by analyzing the faint distortions of light caused by the web's gravitational pull, scientists have created detailed maps of dark matter distribution, revealing the web's intricate filaments. But the cosmic web isn't just about the filaments, it's also defined by what's not there. Enter cosmic voids, vast regions of space that are eerily empty, containing few galaxies or stars. These voids are the yin to the web's yang, the empty spaces between the threads of the cosmic tapestry. While they might seem like nothingness, they play a crucial role in shaping the universe's structure. So, what makes these voids so important? Stay with us as we explore how these cosmic deserts influence the evolution of galaxies and the large-scale structure of the universe itself. Let's take a step back and look at the cosmic web from a new perspective, not at the threads that make it up, but at the spaces in between. These are cosmic voids, vast regions of emptiness that stretch across the universe, often spanning hundreds of millions of light years. To put it simply, if the cosmic web is a network of highways connecting galaxies, then voids are the open deserts between them, spaces so empty they seem almost alien in their silence. But how do these voids form? It all comes down to the universe's earliest moments. After the Big Bang, tiny fluctuations in density caused matter to clump together in some regions while leaving others nearly empty. Over billions of years, gravity pulled matter into filaments, leaving behind these vast, underpopulated regions. Think of it like a foam of soap bubbles. The bubbles themselves are the voids, while the soapy film between them represents the dense filaments of the cosmic web. Despite their emptiness, voids are far from insignificant. In fact, they play a crucial role in shaping the universe's structure. The galaxies and clusters along the web's filaments are pulled into place by the gravitational influence of these voids, like marbles rolling toward the edges of a bowl. This gravitational tug-of-war helps define the web's intricate pattern, ensuring that matter isn't distributed evenly, but instead clumps together in the threads and nodes we observe. Voids also have a surprising connection to the universe's expansion. Because these regions contain so little matter, they're less affected by gravity's pull, allowing dark energy to dominate. As a result, voids expand faster than the dense regions of the web, stretching the fabric of spacetime itself. It's as if the universe is blowing up a balloon, with the voids growing larger while the filaments are pulled taut. But here's where it gets even more fascinating. Voids aren't completely empty. Scattered within them are a few isolated galaxies, often referred to as void galaxies. These galaxies are like cosmic loners, drifting in the vast emptiness far from the bustling clusters of the web. Studying these galaxies gives scientists a unique window into how the environment of a void affects star formation and galaxy evolution. So, while cosmic voids might seem like nothingness, they're actually full of surprises. They're the yin to the web's yang, the empty spaces that give the universe its structure and shape. Without them, the cosmic web wouldn't be the intricate, awe-inspiring network we know today. Now, let's shift our focus from the voids to the galaxies that light up the web's filaments. These galaxies aren't just random points of light, they're the vibrant hubs of the cosmic web, where stars are born, die, and shape the very fabric of the universe. Galaxies are the jewels of the cosmic web, brilliant, shimmering nodes that light up the dark threads of this vast network. Each galaxy is a city of stars, a swirling hub of gas, dust, and billions of suns, all held together by gravity and shaped by the invisible hand of dark matter. But how do these galaxies come to be, and what role do they play in the cosmic web's grand design? It all begins with gravity. As the universe expanded after the Big Bang, tiny ripples in the density of matter grew over time, pulling gas and dark matter into dense clumps. These clumps became the seeds of galaxies, with gravity acting as the sculptor, shaping them into the diverse forms we see today. Some galaxies, like our own Milky Way, are elegant spirals, their arms swirling with young, hot stars and glowing nebulas. Others are elliptical, smooth and round, filled with older, cooler stars. And then there are irregular galaxies, chaotic and unpredictable, defying the usual classifications. But galaxies don't exist in isolation. They're woven into the filaments of the cosmic web, forming clusters and superclusters that stretch across billions of light years. These clusters are the bustling metropolises of the universe, where hundreds or even thousands of galaxies gather, bound together by gravity. One of the most distant and massive clusters ever discovered, known as SPDCLJ 06155,746, lies over 7 billion light-years away. Its sheer size and brightness make it a beacon in the cosmic web, offering a glimpse into how these structures evolve over time. Galaxies within these clusters are constantly interacting, colliding, and merging, a cosmic dance that shapes their evolution. When two galaxies collide, their stars rarely crash into each other. Space is vast, after all, but their gas clouds do, triggering bursts of star formation. These galactic mergers can also feed the supermassive black holes at the centers of galaxies, igniting them into brilliant quasars that outshine entire galaxies. Speaking of supermassive black holes, they play a crucial role in the life of a galaxy. Lurking at the heart of nearly every galaxy, these immense gravitational wells influence their surroundings in profound ways. They can heat up gas, preventing it from collapsing into new stars, or spew out jets of particles that shape the galaxy's structure. In some cases, they even regulate the growth of the galaxy itself, creating a delicate balance between creation and destruction. As we zoom out and look at the cosmic web as a whole, it's clear that galaxies are more than just points of light. They're the vibrant, dynamic hubs of this immense structure. Each one tells a story of formation, evolution, and interaction, a story written in the language of gravity, dark matter, and the forces that shape the universe. And while galaxies may seem like isolated islands in the vast ocean of space, they're deeply connected, part of a network that spans the cosmos. From the smallest dwarf galaxy to the largest cluster, each one is a thread in the cosmic web, a shining jewel in the tapestry of the universe. Now, let's turn our attention to the enigmatic forces that bind these galaxies together, dark matter and gravity, and explore how they shape not just individual galaxies, but the entire cosmic web itself. At the heart of nearly every galaxy lies a cosmic powerhouse, a supermassive black hole, an object so dense and massive that not even light can escape its pull. These enigmatic giants are more than just destructive forces. They're the engines that drive the evolution of galaxies and shape the very fabric of the cosmic web. Imagine them as the beating hearts of galaxies, pumping energy and matter into their surroundings, influencing everything from star formation to the large-scale structure of the universe itself. So, how do these supermassive black holes come to be? The answer lies in the early universe, when the first galaxies were forming. As matter clumped together under gravity's pull, some regions became so dense that they collapsed into black holes. Over billions of years, these black holes grew by swallowing surrounding gas, dust, and even other black holes, becoming the supermassive behemoths we observe today. Take, for example, the black hole at the center of the galaxy Messier 87, or M87. This monster weighs in at around 6.5 billion times the mass of the Sun, a staggering figure that defies imagination. But black holes aren't just cosmic vacuum cleaners, they're also creators. As gas spirals into a black hole, it forms a glowing disk of material called an accretion disk. Friction heats this disk to incredible temperatures, causing it to emit vast amounts of energy. In some cases, this energy is channeled into powerful jets that shoot out from the black hole's poles, traveling at nearly the speed of light. These jets can extend far beyond their host galaxies, carving out vast bubbles in the surrounding gas and influencing the formation of stars and galaxies across millions of light years. Here's where it gets even more fascinating. Supermassive black holes are deeply connected to dark matter. While dark matter provides the gravitational scaffolding for the cosmic web, black holes help regulate the flow of gas and energy within it. They act like cosmic traffic controllers, directing how matter moves through the web's filaments and nodes. Without black holes, galaxies might not form in the way we observe, and the cosmic web's intricate structure could look very different. One of the most mind-blowing discoveries in recent years is the detection of a black hole over 10 billion times the mass of the Sun, located in a galaxy nearly 13 billion light-years away. This means it formed when the universe was just a fraction of its current age, challenging our understanding of how such massive objects could grow so quickly. As we look at the cosmic web as a whole, it's clear that supermassive black holes are more than just galactic oddities. They're integral to the universe's evolution. They shape the growth of galaxies, influence the distribution of matter, and even play a role in how the cosmic web itself evolves over time. Now, let's zoom out even further and consider how the cosmic web, with all its galaxies, filaments, and black holes, contributes to the universe's grand story, a story that began with the Big Bang and continues to unfold in ways we're only beginning to understand. The cosmic web isn't just a snapshot of the universe's structure, it's a living, evolving story, one that began with the Big Bang and continues to unfold across billions of years. From the earliest moments of the cosmos, this vast network has been the stage on which the universe's grand drama has played out, shaping galaxies, clusters, and the very fabric of space-time itself. But how exactly has the web influenced the universe's evolution, and what can it tell us about where we're headed? To understand this, let's rewind to the universe's infancy. In the first moments after the Big Bang, the cosmos was a seething, chaotic sea of energy and particles. Tiny ripples in this primordial soup, fluctuations so small they'd be invisible to the naked eye, held the seeds of the cosmic web. Over time, gravity began to pull these ripples into denser clumps, creating the first threads of dark matter that would become the web's backbone. As the universe expanded and cooled, gas flowed along these threads, forming the first stars and galaxies. This process wasn't random, it was guided by the web's intricate structure. Galaxies didn't form in isolation, they clustered along the filaments, drawn together by gravity's invisible hand. These clusters, in turn, became the nodes of the web, bustling hubs of cosmic activity where galaxies collided, merged, and gave birth to new stars. Over billions of years, the web grew more complex, its filaments stretching across the universe and connecting everything in a delicate yet vast network. But the cosmic web's role goes beyond just shaping galaxies. It's also a key to understanding the universe's past. By studying the distribution of galaxies and the web's filaments, scientists can trace the universe's history, uncovering clues about how it evolved from a hot, dense state to the diverse cosmos we see today. It's like reading a cosmic history book, with each galaxy and cluster a chapter in the story of the universe. And the story isn't over. The web continues to evolve, shaped by the interplay of gravity and dark energy. As dark energy accelerates the universe's expansion, it's stretching the web's filaments, pulling galaxies farther apart and thinning out the threads that connect them. This raises profound questions about the universe's ultimate fate. Will the cosmic web continue to grow, or will it eventually unravel, leaving galaxies isolated in an ever-expanding void? As cosmologist Carlos Frenk once said, "The cosmic web is the universe's blueprint, a map that reveals not just where we've come from, but where we're going. This quote captures the web's significance. It's not just a structure, it's a guide to understanding the universe's past, present, and future. By studying the cosmic web, we're not just exploring the universe's architecture, we're uncovering the story of its evolution from the Big Bang to the distant future. It's a story of growth, change, and endless possibility, one that challenges us to think bigger and ask deeper questions about the nature of reality. Now, as we look ahead, let's consider what the cosmic web might reveal about the universe's ultimate destiny, a question that takes us to the very edge of what we know and into the realm of what we can only imagine. The fate of the universe is one of the most profound questions we can ask, a question that takes us beyond the boundaries of what we know and into the realm of possibility. If the cosmic web is the universe's architecture, then its future holds the key to understanding how everything might end. Scientists have proposed several theories about the universe's ultimate destiny, each one more fascinating and unsettling than the last. And at the heart of these theories lies the cosmic web, its structure shaped by the invisible forces of dark matter and dark energy. One of the leading scenarios is the Big Freeze, also known as the heat death. In this scenario, the universe continues to expand forever, driven by dark energy's relentless push. Over trillions of years, galaxies grow farther apart, stars burn out, and the cosmic web stretches thinner and thinner. Eventually, the universe becomes a cold, dark, and empty place, with no energy left to form new stars or sustain life. It's a haunting vision, one where the once vibrant threads of the cosmic web fade into nothingness. Then there's the Big Rip, a more dramatic end where dark energy's influence grows stronger over time. As the universe expands faster and faster, the cosmic web's filaments are stretched beyond their limits. Galaxies are torn apart, stars are ripped from their orbits, and even atoms are pulled into pieces. In this scenario, the universe doesn't just fade, it unravels completely, leaving behind a fragmented, chaotic void. On the flip side, some theories suggest the universe might collapse in on itself in a big crunch. If dark energy's influence weakens over time, gravity could eventually reverse the expansion, pulling everything back together. Galaxies would merge, stars would collide, and the cosmic web would crumple into a dense, hot singularity, a cosmic reset that could spark another Big Bang. But what does this mean for the cosmic web itself? Could it survive the universe's end, or would it be destroyed along with everything else? The answer depends on which scenario plays out. In the Big Freeze, the web's filaments might persist for billions of years, slowly fading as the universe grows colder. In the Big Rip, they would be torn apart, their delicate threads unable to withstand the forces pulling them apart. And in the Big Crunch, the web would collapse, its structure lost in the chaos of a collapsing universe. These scenarios aren't just about the fate of the universe, they're about the fate of everything within it. Galaxies, stars, planets, and even life itself are tied to the cosmic web's structure. If the web unravels or collapses, so too does the framework that holds the universe together. It's a reminder of how deeply interconnected everything is, from the smallest atom to the largest galaxy cluster. But what if the cosmic web isn't the end of the story? Some theories suggest that our universe might be just one of many in a multiverse, a vast collection of parallel universes, each with its own cosmic web. In this view, the fate of our universe might be just one chapter in a much larger story, with endless possibilities stretching beyond the horizon of what we can observe. As we ponder these cosmic questions, one thing becomes clear: the cosmic web isn't just a structure, it's a lens through which we can explore the universe's past, present, and future. It's a reminder of how much we've learned and how much we have yet to discover. And while the universe's ultimate fate remains a mystery, the journey to uncover it is what keeps us looking up at the stars, wondering what lies beyond the boundaries of the known. What if our universe is just one thread in a much larger tapestry, a single drop in an infinite cosmic ocean? This is the tantalizing idea behind the multiverse theory, the notion that our universe might be just one of countless others, each with its own unique laws of physics, galaxies, and perhaps even life. While the cosmic web connects everything within our observable universe, could it also extend beyond, weaving together a multiversal network so vast it defies comprehension? The concept of a multiverse isn't new. For decades, physicists and cosmologists have speculated about the existence of parallel universes, driven by theories like string theory, quantum mechanics, and the idea of cosmic inflation. These theories suggest that our universe might be just one bubble in a frothy sea of universes, each one expanding and evolving independently. Imagine the cosmic web not as a single network, but as part of an even grander structure, a multiversal web where filaments of galaxies and dark matter stretch across dimensions we can't yet perceive. But how could such a multiverse work? One possibility is that other universes exist in higher dimensions, invisible to us but connected through the fabric of space-time. In this view, the cosmic web's filaments might extend beyond our universe, linking to other realms in ways we can't yet detect. It's like trying to imagine a two-dimensional creature living on a piece of paper. It would have no concept of the three-dimensional world around it, even though that world exists. Similarly, we might be surrounded by other universes, separated by dimensions we can't access. The idea of a multiverse isn't just science fiction, it has real scientific implications. For example, the cosmic microwave background, the faint afterglow of the Big Bang, shows tiny ripples that some scientists believe could be evidence of collisions between our universe and others. These cosmic bruises might be the fingerprints of a multiverse, offering a tantalizing glimpse into what lies beyond our cosmic horizon. Yet, proving the existence of a multiverse is no simple task. As physicist Brian Greene once said, the multiverse is a profound idea, but it's also a deeply challenging one. It asks us to accept that there might be realms of reality we can never see or touch, yet which shape the very nature of our existence. This quote captures the essence of the multiverse theory. It's a concept that stretches the limits of our imagination and challenges the boundaries of science. The philosophical implications of a multiverse are just as profound as the scientific ones. If our universe is just one of many, what does that mean for our place in the cosmos? Are there other versions of us, living out different lives in parallel realities? Or are we unique, a one-time occurrence in an infinite sea of possibilities? These questions push us to think beyond the confines of our own universe, exploring the nature of reality itself. As we consider the possibilities of a multiverse, one thing becomes clear: the cosmic web might be more than just the structure of our universe. It could be the key to understanding a much grander reality. Whether or not we ever prove the existence of other universes, the idea of a multiverse challenges us to think bigger, to question what lies beyond the boundaries of the known, and to embrace the infinite possibilities of the cosmos. Now, let's take a step back and reflect on what all of this means for our understanding of the universe and our place within it. As we explore the cosmic web, it's impossible not to confront the profound philosophical questions it raises. What is reality, truly? Is the universe we perceive just one layer of a much deeper, more intricate truth? These are the kinds of questions that have fascinated thinkers for centuries, from ancient philosophers to modern scientists. The cosmic web doesn't just challenge our understanding of the universe, it challenges our understanding of ourselves. Consider this: the web's filaments stretch across billions of light years, connecting galaxies, clusters, and voids in a vast, interconnected network. Yet, as vast as it is, it's still only a fraction of what's out there. Beyond the observable universe lies the unobservable, a realm we may never fully comprehend. This raises a humbling question: are there limits to what we can know? Philosophers like Emmanuel Kant pondered the boundaries of human understanding, suggesting that some truths might forever lie beyond our grasp. The cosmic web seems to echo this idea, reminding us that the universe is far grander and more mysterious than we can ever fully understand. And yet, this mystery isn't something to fear, it's something to embrace. As physicist Richard Feynman once said, "I would rather have questions that can't be answered than answers that can't be questioned." This sentiment captures the essence of our quest to understand the cosmic web. It's not just about finding answers, it's about asking better questions, about pushing the boundaries of what we know and daring to imagine what lies beyond. These questions don't just shape our scientific pursuits, they shape how we see ourselves in the grand scheme of things. If the cosmic web is the universe's architecture, then what role do we play within it? Are we merely observers, tiny specks in an infinite cosmos, or do we have a more active role in shaping the universe's story? These are questions without easy answers, but they invite us to reflect on our place in the cosmos and the legacy we leave behind. The cosmic web also challenges our perception of existence itself. If the universe is a vast network of interconnected threads, does that mean everything is connected in ways we can't yet see? Could the actions of one galaxy, or even one star, ripple across the web and influence events billions of light years away? These ideas blur the line between science and philosophy, inviting us to think about the universe not just as a physical structure, but as a living, evolving entity. It's not just scientists and philosophers who are inspired by these ideas. The cosmic web has captured the imagination of artists, writers, and thinkers across cultures. From ancient myths about the world tree to modern science fiction exploring interdimensional networks, the concept of a vast, interconnected universe resonates deeply with our collective imagination. This cultural impact reminds us that the cosmic web isn't just a scientific discovery, it's a story that speaks to something fundamental about the human experience. As we ponder these questions, one thing becomes clear: the cosmic web isn't just a map of the universe, it's a mirror reflecting our deepest curiosities, fears, and aspirations. It challenges us to think bigger, to question what we know, and to embrace the beauty of the unknown. And perhaps in doing so, it helps us see not just the universe, but ourselves in a new light. Now, let's turn our attention to how these philosophical and cultural reflections shape the way we study and understand the cosmic web, and how they inspire us to keep exploring, no matter how far the journey takes us. The cosmic web isn't just a scientific concept, it's a source of endless inspiration, a muse that has captivated artists, writers, and dreamers across generations. From the swirling brushstrokes of a painting to the intricate plots of science fiction, the web's vast, interconnected beauty has found its way into our culture, sparking creativity and inviting us to imagine the universe in new and profound ways. Take, for example, the work of visual artists like Nas, own data visualizers who transform raw astronomical data into stunning images of the cosmic web. These aren't just scientific tools, they're works of art, revealing the web's filaments and voids in vibrant color and detail. Artists like these bridge the gap between science and creativity, helping us see the universe not just as a collection of facts, but as a tapestry of wonder. The cosmic web has also woven its way into literature and film, becoming a symbol of connection and mystery. In science fiction, it often serves as a metaphor for the interconnectedness of all things. Think of stories like Isaac Asimov's Foundation series, where a galactic empire is held together by a web of trade routes and alliances, or the Star Trek universe, where the idea of a subspace web connects distant civilizations. These narratives reflect our fascination with the cosmic web, using it as a backdrop to explore themes of unity, exploration, and the unknown. Even in visual media, the cosmic web has left its mark. Films like Interstellar and Arrival use its imagery to evoke a sense of awe and scale, reminding us how small we are in the grand scheme of things. And in video games like No Man's Sky, players can traverse a procedurally generated universe that mimics the web's structure, offering a virtual playground for exploration and discovery. But why does the cosmic web resonate so deeply with our imagination? Perhaps it's because it mirrors something fundamental about the human experience: our desire to connect, to understand, and to find meaning in the vastness of existence. The web's filaments, stretching across the cosmos, remind us that everything is linked, from the smallest atom to the largest galaxy cluster. It's a concept that transcends science, touching the realms of philosophy, spirituality, and art. This cultural impact isn't just about storytelling, it's about how we see ourselves in the universe. The cosmic web challenges us to think beyond our individual lives, to consider our place in a network that spans billions of light years. It's a reminder that we're part of something much larger, a thread in the tapestry of existence. And now, as we look to the future, the cosmic web is inspiring not just artists and writers, but everyday people too. Through citizen science projects like Galaxy Zoo, anyone can contribute to mapping the universe, helping scientists uncover the secrets of the cosmic web. These projects invite us to become active participants in the story of the cosmos, bridging the gap between science and society. So, how does the cosmic web inspire you? Does it spark your curiosity, your creativity, or your sense of wonder? As we continue to explore its mysteries, let's remember that the web isn't just a scientific discovery, it's a cultural phenomenon, a source of inspiration that connects us all across time and space in the endless quest to understand the universe. The cosmic web isn't just a playground for professional scientists, it's a frontier where anyone can contribute to groundbreaking discoveries. Thanks to the rise of citizen science projects, amateur astronomers and curious enthusiasts around the world are playing a vital role in mapping and understanding this vast cosmic network. These projects open the door for everyday people to become part of something much larger, connecting them to the universe in ways that are both personal and profound. Take, for example, the Galaxy Zoo project, one of the most successful citizen science initiatives to date. Launched in 2007, Galaxy Zoo invites volunteers to classify galaxies based on images captured by telescopes like Hubble and the Sloan Digital Sky Survey. By analyzing the shapes, colors, and structures of these galaxies, participants help scientists identify patterns in the cosmic web's filaments and voids. What's remarkable is that these volunteers aren't just passive observers, they've made real discoveries, from identifying rare galaxy types to uncovering evidence of galactic collisions. But Galaxy Zoo is just the beginning. Other projects, like Zooniverse and the Dark Energy Survey, allow volunteers to sift through vast amounts of astronomical data, searching for clues about the cosmic web's structure and evolution. These platforms don't require a background in astrophysics. They provide tutorials and tools to guide participants, making the process accessible to anyone with an internet connection and a curious mind. The impact of these projects goes beyond the data itself. By involving the public in scientific research, citizen science fosters a deeper connection to the cosmos. It's a reminder that the universe isn't just for scientists, it's for all of us. And as more people participate, the collective effort helps accelerate discoveries, offering new insights into the cosmic web's mysteries. One inspiring example is the discovery of Hanny's Voorwerp, a mysterious green cloud of gas found by Dutch schoolteacher Hanny van Arkel while participating in Galaxy Zoo. This unusual object, which turned out to be a light echo from a quasar, had been overlooked by professional astronomers but was spotted by an enthusiastic volunteer. It's a testament to the power of collaboration and the potential for anyone to make a meaningful contribution to science. As we look to the future, citizen science is poised to play an even bigger role in cosmic web research. Advances in technology, like machine learning and artificial intelligence, are making it easier to process and analyze the massive amounts of data generated by telescopes. But these tools still rely on human intuition and creativity to uncover patterns and anomalies that algorithms might miss. By combining the power of human curiosity with cutting-edge technology, we're creating a new era of discovery, one where everyone can be a part of unraveling the universe's secrets. The future of cosmic web research isn't just about bigger telescopes or more advanced simulations, it's about collaboration. It's about bringing together professional scientists, amateur astronomers, and curious minds from all walks of life to explore the cosmos together. And as we continue to map the cosmic web, we're not just uncovering the universe's structure, we're building a community of explorers, united by a shared sense of wonder and a desire to understand the mysteries that stretch far beyond our horizon. Now, let's turn our gaze to the cutting-edge technologies and ambitious projects that are shaping the future of cosmic web research, and how they're bringing us closer to answering some of the universe's biggest questions. The future of cosmic web research is brimming with promise, driven by groundbreaking technologies and ambitious missions that are set to revolutionize our understanding of the universe. Imagine a world where we can map the entire cosmic web in unprecedented detail, tracing its filaments and voids across billions of light years. This isn't science fiction. It's the goal of some of the most advanced telescopes and space missions currently in development. One of the most exciting projects on the horizon is the Nancy Grace Roman Space Telescope, set to launch in the mid-2020s. This next-generation observatory will peer deeper into space and time than ever before, capturing images of distant galaxies and mapping the distribution of dark matter with remarkable precision. By analyzing how light bends around invisible masses, the Roman telescope will reveal the cosmic web's hidden structure, offering new insights into how it formed and evolved. But it's not just about seeing farther, it's about seeing differently. The European Space Agency's Euclid mission, launching in the coming years, is designed to study the universe's expansion and the role of dark energy in shaping the cosmic web. By measuring the redshifts of billions of galaxies, Euclid will create a three-dimensional map of the web, shedding light on how dark energy has stretched its filaments over time. This mission could help answer one of the most pressing questions in cosmology. What is driving the universe's accelerated expansion? Closer to home, ground-based observatories like the Vera C. Rubin Observatory in Chile are set to transform our understanding of the cosmic web. Equipped with the largest digital camera ever built, Rubin will scan the entire southern sky every few nights, capturing images of billions of galaxies. This immense dataset will allow scientists to track the web's evolution over time, revealing how galaxies form, cluster, and interact within its threads. These advancements aren't just about technology, they are about possibility. With tools like these, we could uncover entirely new forms of matter or energy that play a role in the cosmic web's structure. Imagine discovering a new type of particle that interacts with dark matter, or finding evidence of exotic physics that challenge our current understanding of the universe. The cosmic web might even hold clues about the nature of dark energy itself, offering a glimpse into the forces that shape the cosmos on the grandest scales. Yet, as we push the boundaries of exploration, we must also consider the ethical implications of our quest. What does it mean to probe the farthest reaches of the universe? How do we balance the pursuit of knowledge with the responsibility to use that knowledge wisely? These questions aren't just philosophical, they are practical. The resources and energy required for these missions come with environmental and societal costs. As we reach for the stars, we must also think about the impact of our actions here on Earth. The future of cosmic web research isn't just about unlocking the universe's secrets, it's about understanding our place within it. With every discovery, we're reminded of how interconnected everything is, from the smallest particles to the largest structures in the cosmos. And as we continue to explore, we're not just mapping the cosmic web, we're weaving our own story into its threads, a story of curiosity, collaboration, and the endless quest to understand the universe. Now, let's turn our attention to how these discoveries might reshape our understanding of the cosmos and what they could mean for the future of humanity itself. As we reach the farthest edges of our exploration, it's worth pausing to ask, what does it mean to pursue knowledge on this scale? The cosmic web isn't just a scientific marvel, it's a mirror reflecting our deepest questions about responsibility, ethics, and the impact of discovery. When we study the universe's largest structures, we're not just uncovering its secrets, we're shaping how we see ourselves within it. And with that power comes a profound responsibility to explore thoughtfully, to share knowledge openly, and to consider how our discoveries might change the world. One of the most immediate ethical considerations is the impact on our worldview. The cosmic web challenges us to think beyond our individual lives, to see ourselves as part of a vast, interconnected network that spans billions of light years. This perspective can be both humbling and inspiring, but it also raises questions about how we treat one another and our planet. If we're all threads in the same cosmic tapestry, what does that mean for how we address global challenges like climate change, inequality, and conflict? The cosmic web doesn't just expand our understanding of the universe, it invites us to rethink our place within it. But with great knowledge comes great responsibility. The tools and technologies we use to study the cosmic web, telescopes, supercomputers, and advanced simulations, are not without their costs. The resources required to build and operate these instruments come with environmental and societal implications. For example, the energy consumption of massive data centers used to process astronomical data contributes to carbon emissions. As we reach for the stars, we must also consider how our actions impact the Earth, ensuring that our pursuit of knowledge doesn't come at the expense of our planet's health. There's also the question of how we share what we learn. The cosmic web is a shared heritage, a story that belongs to all of humanity, yet access to scientific knowledge and the tools to explore it isn't always equitable. How can we ensure that discoveries about the universe benefit everyone, not just a privileged few? Initiatives like open access journals, public science outreach, and citizen science projects are helping bridge this gap, but there's still work to be done. The more we democratize access to knowledge, the more we can inspire future generations to explore, question, and dream, and then there's the potential for misuse. The technologies developed to study the cosmos, from advanced imaging to artificial intelligence, could have applications beyond astronomy. While these tools hold incredible promise, they also carry risks if used irresponsibly. How do we balance the pursuit of knowledge with the need to safeguard against unintended consequences? It's a question that extends far beyond the cosmic web, touching on everything from data, privacy, to the ethics of AI. So, how should we approach the mysteries of the universe? The answer lies in a commitment to responsible exploration, one that values curiosity, collaboration, and care. As we uncover the secrets of the cosmic web, we must also consider how those discoveries shape our world and our future. It's not just about understanding the universe, it's about understanding ourselves and our role within it. As we reflect on the journey we've taken so far from the filaments of the cosmic web to the forces that shape it, from the galaxies that light it up to the ethical questions it raises, one thing becomes clear: the universe is more than a scientific puzzle. It's a story, a mirror, and a challenge. It invites us to look outward and inward, to explore not just the cosmos, but the very nature of our existence. And as we continue this journey, let's remember that the ultimate question isn't just what lies beyond the observable universe. It's how we, as explorers, choose to navigate the vast and wondrous unknown. As we come to the end of this journey through the cosmic web, let's take a moment to reflect on the incredible story we've uncovered. From its intricate filaments of galaxies and dark matter to the vast voids that stretch between them, the cosmic web is more than just a structure. It's the backbone of the universe itself. It connects everything, from the smallest star to the largest galaxy cluster, in a delicate yet awe-inspiring network that spans billions of light years. We've explored how this colossal framework formed from the tiniest ripples in the early universe, shaped by the invisible forces of dark matter and dark energy. We've seen how galaxies, stars, and even supermassive black holes are woven into its threads, each playing a role in the web's evolution, and we've marveled at the tools scientists used to study this vast network. From telescopes that peer into the farthest reaches of space to supercomputer simulations that recreate the universe's birth. But the cosmic web isn't just a scientific marvel, it's a lens through which we can explore some of the universe's deepest mysteries. It challenges us to think beyond what we can see, to question the nature of dark matter and dark energy, and to ponder the ultimate fate of the cosmos. It invites us to consider what lies beyond the observable universe, in realms we may never fully understand. This journey has also reminded us of the power of human curiosity and collaboration. From professional scientists to citizen scientists around the world, the quest to unravel the cosmic web's secrets is a testament to our shared desire to explore, to learn, and to connect with the universe in profound ways. As we wrap up this exploration, let's carry these insights with us: the wonder of the cosmic web, the questions it raises, and the possibilities it opens. The universe is vast, mysterious, and endlessly fascinating, and the cosmic web is just one chapter in its grand story. Now, as we transition to the final part of our journey, let's tie everything together and consider what all of this means not just for our understanding of the cosmos, but for how we see ourselves within it. The cosmic web isn't just a map of the universe, it's a mirror reflecting our place in the grand tapestry of existence.